Hi, my name is Jamin Hareshbhai Khadela, and today I'm going to present my research poster, and its title is Spacecraft Analysis. So, my research focuses on understanding like why launch vehicle and spacecraft fail, and how computer-based control system, like both hardware and software, play a big role in these failures. So, my goal is to show how analyzing past incidents can support safer and more reliable spacecraft mission. So now I'm going to introduce my topic. So if I talk about space technology, then it is advancing very fast. So and still failures happens during launch and orbital operations or during the mission itself. So these failures can result in a large financial losses and lost missions, and sometimes even safety risk also. And because of this all, it is very important to study the causes of failure and study the patterns and contributing factors behind these failures. So by doing this, he can improve the design of spacecraft and make system more reliable and reduce the chance of mission failure. And my research mainly focuses on orbital carrier rockets and spacecraft, like especially how computer-based control system like sensors and softwares and automated system can affect the mission success. So let me talk about rational. So space missions operate under very extreme environmental conditions, like they rely heavily on complex systems that work together, such as propulsion system and navigation and communication and onboard computers. So if any of these subsystem fail, it can cause major issues. For example, if propulsion malfunction might stop, then the rocket if a propulsion malfunction might stop the rocket from reaching orbit, and software error might send incorrect commands, and if there is a sensor error, then it problem might be give wrong readings and cause the spacecraft to react incorrectly. So by studying historical launch and spacecraft failures, we can find the patterns, like how it is previously we can see the patterns. So these patterns help engineers design better system and uh, prevent similar incidents in the future. So my project especially focus on automation and software driven subsystem, and because modern spacecraft depend heavily on digital controls, as I said earlier, that it depends on more like sensors and software and automated system. So mistake in these systems can lead to big problems. So it is very essential to understand them. And uh, if I talk about the figure, then it shows the percentage of spacecraft failure by different causes. Like there is a 40% of propulsion failure, and then 20% of structural failure, and also 15% of avionics failure and software causes, and there are some other 10% causes. So if I talk about aims and objectives, then the main aim of my research is to analyze the different risks that lead to launch vehicle crashes and spacecraft failures. So to talk about objectives, there is three key objectives. So first one is build a database of past orbital rocket and spacecraft failures. So this includes collecting the publicly available data about launch failures, the subsystems involved, and the mission stage when the failure occurred, and the suspected causes as well. The second one is evaluate the causes using FMEA. So FMEA means failure mode, effects, and critical analysis. So it helps the identifying which types of failure happen most often and how serious they are. So it also shows which subsystem are most vulnerable. And the third objective is analyze the influence of computer-based control system. So here I study like how hardware and software issues like computer errors or sensor faults or software bugs contribute to the failures. Sorry. So the purpose is to understand how digital system affect mission success and where improvement can reduce the risk. So uh, let me talk about the different chart, which is propulsion system failures. So it is showing the percentage of which cause the propulsion system failure. And if I talk about methodologies, then there is 5 main methods which I showed here. First one is data collection. So I gathered launch incident reports, test summaries, and technical documents from public sources and organized them into a structured database. The second method is descriptive analysis. So in this I analyzed how often failure occurs and in which vehicle or subsystem and during which phase of the mission. And the third one is failure analysis. So this step involves assigning severity and probability scores and calculating risk priority numbers. So this helped identify the most critical types of failure. And the fourth method is control system focus. So I studied failure specifically linked to the software and avionics, such as control system faults or sensor failure and communication breakdowns. And the fifth one is synthesis and validation. So in this finally I combined the results and checked them against expert reviews and statistical methods. So if I talk about ethical consideration, then in this study I used only publicly available and non-sensitive data to make sure I did not violate any confidentiality or access restricted information. So all incidents are described responsibly, so that no individual or organization is blamed. And I also considered the broader ethical impacts of spacecraft failure, such as risk to people or environmental hazard from launch debris or explosion, and the importance of using technologies finding to improve the safety rather than create new risk. And the last one is risk and mitigation. So there is few risk I guess, and the first risk is propulsion system. So to avoid this, we can perform more rigorous engine testing, and we can use redundant sensor and can apply real-time engine health monitoring. The second risk I see is structural failure. So to prevent this, we can use better materials and improve load testing and quality control. And third risk is avionics and software. So to avoid this, we can strengthen the software testing, and you can use watchdog timers, and we can use we can improve error handling routines. The other risk is human or procedural errors. So to prevent this, we can use detailed checklist, and we can improve training and verification steps, and we can conduct more simulations. And other risk is ground support equipment. So to prevent this, we can maintain the fueling and electrical system properly, and we can use real-time monitoring. So by implementing these strategies, many potential failure can be prevented, and so it can reduce mission risk and improve spacecraft reliability. So overall, my only goal is to support safer, more efficient, and more successful space mission in the future.